Carrying on, it's the 27th of June, 2023, and here it's been a few days talking about inequalities and their deconstructive account as an equality and equality as a type of inequality that's not satisfied. Or when they're greater than or less than, and then there's equals, and then there's the composite conditions, greater than and equals and less than and equals, and then whether or not they're exclusive, and then that greater than and less than, of course, are generally considered exclusive of each other. Then there's the notions of with increasing and decreasing in terms of functions, as that is a property that over the course, like in a continuous function, that the elements that are close in the domain are close in the range in the topology, according to the neighborhoods, and differences, and that there are functions that are increasing, that they never reduce. As far as that in a given domain, like a dimension, there's basically a property in it that as it goes from 0 to infinity, it's strictly, constantly increasing and decreasing. So even the very idea of increasing and decreasing, or and then as to whether strictly increasing means also never just flat and level, because sometimes increasing will just mean non-decreasing, and decreasing just means non-increasing. And one can further emphasize the usual intent and meaning that increasing is nowhere decreasing and always in fact increasing, and vice versa. And there's that when things are constant, then that reflects, for example, whether it's constant or whether it's this constant increasing, and any differences from that. Anything about being greater or less than linear, where basically constant reflects 0 and increasing reflects in x, it reflects x, the expression about constant increasing and decreasing, in what result then in definitions of both geometrical and algebraic and numeric, or each of. When one says both, it's meant to include each. And then, for example, when someone says neither and nor, and then you can also, whether you have to say nor and then whether contains and nor. Now this is just something I was looking at today, wondering, is it really necessary to say contains again? For example, does it extend in this manner? Well, what does that mean? It's just about that these are words, and these are these definitional dynamics, and these are the definitions, and then in accordance with anything that we have that's a mathematical word, it should more or less have the same meaning in English or a natural language. I think it's lucky that it's in English. It's the only language I can really say that I know thoroughly. And so that said, though, it really is a pretty key thing that over time that it results that most all mathematical objects are related to natural language words from various natural languages. And so these definitions serve everybody very well by keeping this same kind of context in place and not requiring technical experts to interpret the meaning of something which has a simple meaning. All right, then. Well, what I would hope to do today is continue reading about the means, the arithmetic mean. We talked about the average and about the moments, and then I was thinking yesterday or today about what's an algebraic mean, and then about the golden mean, which is about root 5 or phi, the golden ratio, and the self-similar, when it's like the ratio between the blocks and the side of a rectangle are the same, and it goes smaller and smaller and smaller. Why that shows up in a lot of things, just as it's kind of it's an emergent type of value that shows up in a lot of things, just because it does. And then I have a pretty good book about it. I'll dig up at some point. And then so that being about the golden mean or means, and then we'll be getting into the geometric mean and harmonic mean. about the notion of the means generally, and then relating the means to these inequalities and bounding the means vis-a-vis these notions of the centralizing properties and the uniformizing or flattening properties, the centralizing and uniformizing. And also as well in these tendencies and propensities about the oscillative and restative that comes back together, and the dissipative and attenuating that falls to the floor and dissipates and attenuates. The idea is that these inequalities help reflect what's going on with equalities. In the usual milieu and in the digital and in the cut and dried or the black and white, that which is monotone, that which has a definite value in one of two Boolean or binary values, true or false, equals oftentimes is the very strong bridge in the center. It's in the theory of words and in the theory of classical ideas, it's true or false and yes and no, and it's the center of things. But when things are of a sort of state of flux, and each free and independent as objects, then this is much more that they come to they meet in part, and whether they are the same or different or near or far or close or distant, that these kinds of terms help reflect as much as equals goes, that there's nothing that's equals. No two things are the same in for example the real world. Now this touches on a couple different concepts. One is called Pauli principle, after W. Pauli or the quantum physicist and his notions that if there's a particle physics in this quantum and discrete physics, that anywhere there's a particle, it's distinct from all the other particles, but it's also indistinguishable from like particles. So particles of a kind don't have any further identity, but they're discernible from each other by their place in space and this and that. So they're equal in their kind of their structure, but they vary in their location. So from this discussion about the context and that the apple in the universe is everything that it is not, it's unique and taken out of the context, it just leaves the place and the relations that all sit and rest on it. It's the same. That still that's just kind of a point for Pauli and Pauli exclusion principle, is that then they can't combine or sit together because there's only one or the other, and it's an apple in a sense. And so that's also gets these notions of equalities and inequalities, or boundaries, and when there's symmetries, the conservation laws either way, that it's either on this side of the boundary or it's on that side of the boundary. Both sides adds up to a constant. Vis-a-vis that when things transport across a boundary and exchange, that those terms are still conserved. Here it's that energy is conserved, but really energy can be in any of a variety of states. It can be in a kinetic state, an electrical state, and various kinds of radio states and the optical states, radionuclear and radiomagnetic and optical, but mostly kinetic and charge on one side and radio optical on the other. And then there's this notion of that the electrons they're fast and classical bodies are slow, but they're still bradyonic and slower than light and arbitrarily moving. And then that the nuclear atoms compared to light has that light is essentially tachyonic, but then it's really as if it's kind of a complement to the contents of the nucleus, and the electroweak and weak nuclear forces that are complements in the standard unified field theory's model of four forces: strong nuclear force, charge, electrical charge, and the weak and electroweak forces, that those form these complements, and they all and exchange things in energy. But then that while we say things are energy, or that they're equivalent to energy or information, that's just when they exchange. These are the elementary deconstructive accounts of quantities that are discussed for a unified field theory, which then has, well, what's left? Gravity? Oh, yeah, gravity is Gravity sits at the bottom and kind of it's a fall gravity, and so the strong nuclear force, or things falling together in the nucleus, really is described by this, instead of that the protons have a binding energy, which they would be working all the time. It's got to be a theory free of any. There's no free lunch. There ain't no such thing as a free lunch. It's also called Tanstaffel, and what it means is there's a conservation of quantities, and so what that means is that there's no perpetual motion device, and it would, because that would mean it had to come from somewhere else, and there's only its neighbors where it can come from and go from. So what this means is then that with the fall gravity and the strong nuclear force together, then you can have charge as a complement of that, because electromotive force works up for the kinetic and stuff like that, and that they live in those realms in the exchange of those bounds and those quantities. And then also the kinematic and kinetic works off heat and stuff like that. The other sometimes big thing in physics that says applies to everything is thermodynamics' second law, and the attenuation according to the second law of thermodynamics. And they call that entropy, but it's kind of a reverse entropy as a quantity, and that's into definitional dynamics. Those two together, and then the other usual quantity outside that is light, like the theory of relativity. And you'll notice a thing missing from Newton's theory and the general theory and the special theory of relativity is the weak and electroweak forces, or the nuclear forces, the radionuclear. So basically, elements and transmutation elements is measured in the half-lives of radioactive isotopes, which is much longer than a person's life usually, except for highly radioactive species of radioactive isotopes. These that have very short half-lives and very quickly convert from one to another form of, according to the atomic numbers, and everything that's held up by the excellent theory of the atomic numbers and the count of protons, and thus the count of electrons. And this kinematic and charge, on this one side that's very strong for the lifetime of the proton and the speed of the electron. And over on light speed, then light and the energy in light and the energy that's contained and released in these reactions, and whether sometimes that represents as well massy and massless, or particles and rays. So in this manner, one can look at about how these things have to equal and not equal and come together and meet in part, and this kind of stuff, helping explain why having all that in terms of being able to frame it in equalities and inequalities makes a lot of sense, because the mathematics is ubiquitously successful in physics. It's mathematical physics. All the models, all the objects, all the elements are in formulas, and that is now that's simplistic, but it is so for the fundamental physics. Now up above that, in all the fields, there's all kinds of the empirical and all kinds of the qualitative about compounds and substances that are known by their properties, not necessarily the constituents, and the behavior of them as parts or pieces, or by the pieces of theory, but only by their organization as a substance or a machine. So, not to be too simplistic, that doesn't mean that mathematical physics isn't part of that. It's just reflects that if you have a mathematical model of all of physics, according to a continuum mechanics, that it still requires this knowledge of these domains, which is still being figured out, chemistry or molecular biology, as in the higher levels of organization, where the definition of entropy and information, which is with thermodynamics, second law, and heat and this kind of thing, as the constantly diminishing thing, what always goes down, kind of like gravity always goes down, heat always goes down, what comes up must goes down. This is about the only oldest old famous principle of restitution and conservation law in since antiquarian times. That then this in the organization and the emergent is reflects what comes in opposites. And then when people assign to that stuff like the quantum consciousness or these notions of what from the fundamental elementary side could be called fringe, because largely then they just get engaged in entirely other qualia that are unrelated or unscientific. At the same time, can be argued about how that's a holistic thing, a way to consider the universe of its parts at a time, and the necessity to do so to have a pretty well-rounded mental model and description of things writ large that's also resistant to meddling, and then when it does changes, is flexible to accommodate its description. These are the kinds of things that are aided by being able then to relate them from the inside and the connectives of these logical models where true and false are paramount and equals is strong, and causality and such relations and notions of implication are strongly connected, and equals is transitive, and a rose is a rose is a rose, and all the things that make do for extensionality in terms of exchange, like money or energy, or in terms of identity, like apples and apples and apples, and types, and all such things which result the classical. That's the classical. That then this dialectic both has the other sides of things. Now there's two sides, and also the fact that there's not just one side. And so this helps just kind of put into place in a philosophical setting, in a cognitive setting, the way these terms can weigh and balance and meter and measure, and that they're constantly doing so. They're free to do so. And then of course, that our theories can limit or restrict that, or make that properly non-logical, properly theoretical, and result how then that way the terms become as strict as need be to be free in their form and in their declaration. Well, this at the same time trying to make sure to never allow that the theory itself could it's not the result of stipulation. It's not like an empirical law. It's like, well, how much water is in a gallon? And it's like, well, it's what fits in the standard jug, and it is. But at the same time, it's like how much water is a drop, you know, and it's in terms of the rest of the universe combined. It is an ocean. So these are the kinds of things that then make for free thought about the whole thing, while both at once not necessarily having to care, because it's abstract, and at the same time that so far as much as you care, it's perfect. And then that the goal of the elementary fundamental physics and elementary fundamental mathematics and this whole foundations bit is in one sense to get to where there's the entire apparatus of the mathematics, and equals and true and false and not equals, and extensionality for intentionality, and types, and all things to do coming up out of is what's today in modern mathematics called axiomatic set theory and descriptive set theory. But then in the mention of something like the quantum consciousness or giant universal brain, or these other theories that writ large basically have all that as like, well, that could just be an abstract thought of a theory in a higher order organization. That's abstract, and then that's left up to the notion, well, if there's a higher power, then there's a higher power, then there's higher power onto higher powers, and then that's just left out to be super scientific, and the space for deity, and then of course that's its reflection in that kind of philosophical question and its answering, which makes why it's fulfilling all such matters of attachment, a belief, and to this higher order connection. For somebody like Einstein's model physicist, then at the same time he needs that on his plate. He's like, I can't eat that idea, and I got to have it on my plate. And so it's got to be available to his senses. And so then again, that's what gets back to axiomatics and descriptive theory. And here what is dynamical modeling in this descriptive differential dynamics. So back to geometric means and arithmetic means and Kanzarov's geometric inequalities. We discussed the average. And so you got sum of the numbers, and we've established that the product of these numbers is only the minimum that's otherwise been established. What it is about when when they're unity. And then there was discussed about that the powers of numbers between 1 and 0 are fundamentally different than the powers of numbers that are greater than 1. The greater ones get larger, and the lesser ones get smaller, and that's a good thing. So we conclude from theorem 7 that the b1s, which made this inverse, making the numbers instead of x and 1 over x, a over b and b over a, that the b's is less than 1 over n to the n, with equality only if b1 equals da 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 equals 1 over n. So that kind of just reflects on this equalities and trying to figure out then what's that line in the middle, and then how things would differ from it with regards to then that complements or the pairwise or overall in a curve and chord, how it's going to be which of these arithmetic means, these geometric means, and these harmonic means, which also are the same, the idea. And then also with these ideas, the algebraic means and other kinds of means. That was one thing I was kind of grasping at, is what does a mean, and how can we get figured what it is. And so when you think of something like the moments, so what's momentous, and how that basically kind of represents the pendulum, or kind of the weight of things in a sense, and it also represents what things will turn on, like an axis or an axle, and then it again talks of their moments in accords with that. And so then the means is both like this exchange in the medium, and then where things will go to. It will go to the mean. If you pour a giant bucket of water in a river, it will, as it goes to the ocean, it will also reach the mean of the height on this riverbed. And where that kind of thing is so, then it represents this quantity that it attains to. It has this dissipative and attenuative property and this restitutive and oscillative property that makes it so constitute as it goes along this thing. So the mean is kind of to be generally defined. It's a pretty loose term. And at the same time, it just means the average. The first and only mean is the average. It's the arithmetic mean. And then the mean, median, and mode are reflect terms about samples. And the average of those, and the middle of those, and the most of those. And then these other means, though, is to be reflected on that they have a geometrical interpretation, and that also they have a quality, a tendency, and propensity that it's just like when attenuation goes to the floor, it's a sort of mean, even though that's like at the end of the world. It's like the waterfall at the end of the world where everything goes, but it's pretty much vertical, and but it's still kind of that level of things, whether it's kind of like got that bounce in it. Now, I mean, this is getting away from technical, except to help clarify that the mean is something that is a property, and it attributes things, it imbues things. And so with that kind of notion, then it's to be considered then in terms of equalities and extensionality, and then how that relates to properties and attributes in types. And when you can say that those predicates are fulfilled, the extensionality of predicates and the transitivity of predicates and the transfer principle of predicates for extensionality and intentionality pretty generally, then this notion of the means is also the middles. So it's very much the middling of things. And the tensities and propensities that for the constitutive and recitative and oscillative, it's the middle and centralizing. For the dissipative and uniformizing and attenuative, it's the uniformizing means. This sample mean of a uniform distribution should vary widely and have no well-defined central tendency. Vice versa. In terms of the original numbers, ... And similarly, the A's over this quantity over 8's is less than equal to that. The original numbers where the H and K, these terms added to the systems of these equations or inequalities, systems of equations here, where it's this system of equations is formulas and inequalities. Looking for a good name for these things generally, I'm not quite sure how to put it, but that these conditions, these expressions and their conditions have that some numbers are provided. So this is just where he's kind of writing out then some more of this in terms of the higher order case, when you're taking the average of a bunch of numbers in the pairwise each, where the proof is to work out in the pairwise to pick one pair and then look for the least one left and do a divide and conquer or the reductio. And so these are just some terms he introduced to make this. Simple application, a theorem for 6 for n.2, prove that x squared is positive. If x squared is positive, then x squared plus 1 over x to the fourth is less than or equal to 1/2. Clearly, if x squared is greater than 0, then x squared is over 1 plus x to the fourth equals 1 over 1 plus x squared for turning that over and then factoring it out and then dividing it into terms in the ways that can be done in terms of the divisor bar and the quantity is on either side of that, and then with regards to those again split out in terms of x fourth plus 1 and x squared, where in a way when it's on the top, he's kind of written the terms in the higher order and then going to the lower order, and what's in the denominator, he's written terms lower order going up to the higher order, 1 plus x to the fourth instead of x to the fourth plus 1. He might have a reason why he would write it that way, even though according to arithmetic and algebra, there's no telling them apart. But in this notation, it might indicate both that he intends to take those terms that way or that he intends to flip them over and inverse them and to maintain in this convention a reminder of it in his notes. These are the kinds of things that one might ascribe to any other use of this. Anything else in the syntax and the expressions and the conditions that's not for, it's not like the form that would be so if they're all sorted by a usual rule or normalized. Anything that's not so normalized may have intent, or anything that would be the same under normalization may just have noise. So it's a room for convention, and also it's aberration. And now he defines the geometric mean. The geometric mean G of n positive numbers, the a sub i's, or a1 through an, is the nth root of their product. So if it's 100 numbers, it's the 100th root that would get small, right, for these numbers, except if they're between 0 and 1, though, and the power a bunch of them, then their root is going to go back to 1. So it's a little bit different algebraically than the average. The average to have is like if you have a bunch of numbers and take their average, it's going to be approximately in the middle of those numbers. But the geometric mean is basically having that if the average of those numbers, it's not exactly, but if the average of those numbers is above 1, the more there are, the higher the value is, and if they're less than 1 but greater than 0, the roots of those, just like the powers of that go to 0, the roots of those go to 1. The theorems 6 and 7 are equivalent to the famous and useful theorem of geometric and arithmetic means. So that what she talked about. About this, the 1 over n bit. Now, and I'm kind of framed it a little bit differently, because it's not exactly tractable that the average is related to the geometric mean at all, because pairwise two numbers can be very different, and so you can't really say that in terms of outliers what those would reflect. In terms of the outlier can totally the outlier basically would adjust the average to where it doesn't make sense. Whether that would or would not so adjust the geometric mean, not necessarily so, because taking the root so many times is a stronger operation than taking the product and dividing by constant. Decimation is when 9/10 of something is struck away. So it's strong. Theorem 8. The geometric mean of n positive numbers is less than or equal to their arithmetic mean. See, now I was thinking about the for negative numbers, that I was thinking for negative n many numbers for a second there, and taking their root is taking their power. Now, I hope you'll please excuse me, as I was taking great license with this expression, and that though taking the root is a very strong operation, is that the roots of the numbers, either above or below, will go towards 1, and the arithmetic mean similarly has this about the identity dimension, and then here about x equals 1, where it's so that then that's just multiplication or division, that these means are as above or below it, and these sorts of balloons about it in the harmonic, that there are various deconstructive accounts to help explain what mechanisms would make so for something to compute the same value of this mean, or things that would go to same value of these means here vis-a-vis these definitions, and then whether these definitions are these definitions are unchanging, but whether these definitions point to other definitions that have more relational input to their dynamics. This would encourage me to understand, because then I'd feel like they were more connected. The geometric mean of n positive numbers is less than or equal to the arithmetic mean. They're only equal if the numbers are equal. He establishes inequality. He names the geometric mean big G, or G, and he names the arithmetic mean A, as it was before, big A, and he establishes that G less than equal to A, and he establishes that the previous theorems helped establish that was so about the products and these numbers being like so. So what I've been doing is be thinking each other combination operations that tend to, and this is about the previous discussion about the operators and the identities and the annihilators, and these various scalar wide points in infinity, or beyond the asymptotic analysis, that there's the notions of the increment and addition, multiplication and powers, exponents and tetration, and then their inverses, the logarithm, the roots, subtraction or decrement, how it works out for these positive numbers first, and then into their symmetries in various cases, whether they're either reflected or translated about those such boundaries. How those, any combination of those represents a way to put them together, to assemble them so they have like properties to these operations. So these sorts of, I'm thinking kind of trying to relate that in terms of moments and means, where the moment reflects like where things will come to, and the means it also has this the meaning of the exchange and how things go, vis-a-vis it's otherwise thought of as the constancy over time, that it's where it's just kind of its level that it finds, and then for these moments that's kind of like where this minima and maxima are. I need to learn about how to understand means and things like the centroid and stuff like that. And the locus, or what become the constant points with things that go around them. All these good old-fashioned terms of geometry that they would have in geometry class and introduce me, like, what is that? The focus, the locus, the centroid I kind of get, center of mass or something like that. But these other ones have their particulars about how they define these systems, and they become the shape and scale parameters or the focal parameters that make for these things, that define for their centralizing and uniformizing what they are, that these are the kinds of things. And so it's described that there's a very general descriptive approach that once you know all these kinds of operations, then when things are defined in terms of operations, you can relate it to each of them. And they exist. We should now describe several geometrical applications of the last three theorems in the chapter. For the present, we content ourselves with two. The first is, of all three-dimensional boxes with a given surface area, the cube has the greatest volume. Let A, B, and C denote the length, width, and height of a box with surface area S and volume V. Clearly, V equals ABC, and S equals 2 times the quantity AB plus BC plus CA. So there's a box, and it's got surface area, the sum of all its sides areas, S, and V is its volume. V equals ABC, and S equals 2, one for each of AB plus BC plus CD, or excuse me, AB plus BC plus CA. The hypothesis that S is fixed means that the sum of the three quantities AB, BC, CA is fixed. This suggests applying theorem 7 or 8 to them. The result is AB dot BC dot CA cube root is less than equal to AB plus BC plus CA over 3. So this is establishing that the geometric mean is less than or equal to the arithmetic mean. And then because AB, BC, CA is the same thing as ABC, the volume squared, because it's got an instance of each term there, that he just writes volume squared to the 1/3. So volume to 2/3 is less than or equal to S, because the expression is over that, and then he has an extra term in that. Thus, he multiplied the right hand side by 2/2. Thus, v is less than or equal to he for v on the left hand side was 2/3. Then he cubed both sides, so it results that v squared equals the right hand side cubed. And then he took the square root of both sides, so it results that v is less than or equal to the right hand side to the 3/2. And so then he's got v less than or equal to the cube of the square root of s over 6. And finally, that equality only holds if AB equals BC equals CA. So here just helps establish that for the geometric mean, that it's just the result of the product of the areas, and it's very much about the geometric mean of a box. And that the arithmetic mean is very much about a box, a cube, and the rectangular, and the parallelepiped for the parallelogon, and these that a box is rectangular, and then that it applies in arbitrarily high dimensions is beyond its usual three-dimensional height, width, depth, meaning, import, application, and generality, and placement and visualization. Then it's also in any of these number of these higher dimensions. So what this gets into the idea is that in the one sense that considers it go out to higher and higher dimensions. And then when you have something like rows and columns of a matrix, then it gets out to pillars and files, these being basically the higher dimensional, what's after rows and columns and pillars and files, and makes up the cubes after the squares and these kinds of things. Then beyond those are called I rows. 1 rows, 2 rows, 3 rows, 4 rows, are these higher order squares that make up in the segments these things. It's that well, firstly, it reminds me that the liter is the deciliter is like 100 cubic centimeters or something like that, and it's just kind of a remarkable unit of measure, because the liter is like 1,000 cubic centimeters. It's a volume, and so it's just 10 centimeters on the side. I mean, the deciliter is just like 1/10 of that. But it's like, as a volume, 1/10 of another volume, they're not really related at all, you know? It's funny. There are various things that get into numerical coincidences, and 10, not just 10 numbers of the fingers and toes, but various numerical coincidences that have to do with 10, and computations about root 5 over 2 or 10 or this or that, which I won't get into exactly right now. That the other thing is the idea that besides going into the higher dimensions, you can just keep it in the one same dimension and stack it out in a pillar. So with the rows and columns making a box, then you can just make another box next to that, as many as need be. And consider that those are the pillar I rows. If necessary, it can be one column, the long column. If this is about rows and columns, oftentimes in the computer sciences, tables and of the relational algebra, the relational database, and you have rows and columns, where rows are relations and columns are attributes or values. And then you have the column vectors themselves in terms of an expression that reflects the contents of a column, and then tuples, whether that's a select list of columns, a column list, of a table-like expression about when there are nulls possible. There's nulls. Null is a data type that's effectively a member of all data types. When such a column's value is nullable, that it as well affects a representation in these I rows. So here the author has described for us this expression in volume and surface area of an n-dimensional box, and he establishes what it is so, and just that there's that the geometric mean establishes that the volume is greater than or equal to this expression in the surface area, s over 6 cube square root, and then that it's only so, and it happens to be so, when they're all equilateral, that it's equals. So. And then the next example is the right circular cylinder of volume V, so it'd be the area of the circle times its height, right? Which has the least surface area, is the one whose diameter is equal to its altitude. So I'm not too sure about this because I'm just not too sure about it yet. I'm just thinking about the singularity theory and the multiplicities, and so the alternate reason from last time about like why is the square having the most area of a quadrilateral for any perimeter, and it's like, well, because in the definition came up was because it's flat or because it's fat that it boxed in or boxed out and made that was the reasoning. And then another one was like, well, it's closest to a circle, and in the regular polygons, that its angles are the same. Obviously, any regular polygon is equilateral. Its sides are the same when its regular angles are the same. I think that's obvious. Yeah, it's pretty obvious. And then they go to circles. So anyways, then it was discussed even besides the non-standard case of the infinitely flattened, where it only has an infinitesimal side length, and so that still maintains a ratio that's 2. That this is this point in infinity after this whole hump where it went away, it drops, and at the end it's just got that one mark that's the same, that adds up somehow, and it does. It's not physically realizable except by objects in such milieu as are like so, and it may attain to that in the effectively unbounded in terms of tendencies and propensities about it. So again, it's contrived. But then for this right cylinder, and the idea that when the diameter and the height are the same, it's the least amount of metal to make the can. I'm not too sure. Denote the surface area, radius, and altitude of volume V by S, R, and H. Now S equals 2 pi R squared plus RH. Establishing that if you unroll the cylinder, that's what he's given as its area. And that the lids are pi R squared. And V equals pi R squared H, which is area pi R squared times H. Therefore, S equals 2 pi times the quantity R squared plus V over pi R equals 2 pi, this quantity R squared plus V over 2 pi R plus V over 2 pi R. We can thus think of S over 6 pi as the arithmetic mean of the three numbers R squared V over 2 pi R and V over 2 pi R. So what he's done is he's taken similarly this volume And he's just saying that these are the three numbers we can thus think of as the arithmetic mean. These numbers r squared v over 2 pi r and v over 2 pi r, so that by theorem 8, s over 6 pi is greater than or equal to v squared over 4 pi squared, 1/3, and then but the right-hand member of this inequality is fixed. Therefore, s is smallest when equality holds. That is, when r squared equals v over 2 pi r, or v equals 2 pi r squared. Thus, s is smallest when 2r equals h. So I'd be thinking of this in a couple different ways. One is that he's computed the area of the sides of the cylinder as of the perimeter, pi times d, times the height of the can, or its width. And so another way would be to think about adding up that all around. And then I just have some questions about then what would happen if in the arbitrarily small. So if there's the case for the square and flattening it, here for the right cylinder, there's this idea of that either the radius goes to 0 or the height goes to 0. What would make that it would end up having one last little ratio before it shrunk down? And as to why are soup cans any more metal than they have to make? Well, maybe it's because by the time you factor in the cost of making a lid, the cost of making a metal, the soup can factory, in all its eminent wisdom, which is this formula, has decided to make a can with so much metal in it for the most volume given the amount of sheet metal. I don't know. But then there's other points is that then in the arbitrarily contrived and as it reflects the distance from the means or the balance of the means, the imbalance of the means, but the balance of the means, that these are the kinds of things that come into play. Otherwise, the author has satisfactorily demonstrated that he's used this mathematical trick to equate some expressions of these quantities on the right-hand side, and then there are algebraic quantities of geometric terms, and then that in terms of the way he computed the area of the side of the can, it's very clear and obvious, but it's kind of like taking a line integral itself, and there are other things to consider about that in terms of the thickness of the metal or the absence thereof, and this kind of thing. Long story short, there's much to be mystified about or left be, but it's satisfactory for now. But there's room for definition that would make clear other things that would have real analytical character, if not in the same space yet, in terms of when things get large or small. And also maybe just in terms of when they're double or half. So then he provides some problems and exercises to solve. And they are that the root of a times b to the n, root n plus 1 is less than or equal to a plus nb over n plus 1. So this might be recalled from earlier discussion about like a plus b over b plus b is less than a over b. And so then in terms of then the pairwise, it's basically just in terms of that this that is left out in front, and it would be a similar kind of divide and conquer approach or iterative approach. And then show that n factorial is less than n plus 1 over 2 quantity to the n. And so this kind of reflects that it's only achieved the equalities of this general identity when the numbers are equal, so showing that they're not, still has that it's just n plus 1 over 2. That's the inequality there. They could be closer bound, first of all, like n plus 0.00000000001 over 2, or otherwise to make it so that it was more closely modeled. And then about this about that the average of the numbers in the factorial they have these different contributions. Now it's so that as the numbers get bigger, they're in the lower level of the pyramid, so they make more. But at the same time, if you just thought of them as like, well, the last one's the end, and it's reflective about some middle where it met or came from, and then, so if you had infinity factorial, again, it wouldn't apply. That's not well defined. No, it's not, unless you have a non-standard framework where it is well defined. It's not standardly well defined. It's an example of that. Otherwise, if you just have a modular Boolean lattice or a Boolean algebra of these objects, like the ring of integers, the finite rings, they go around in the integral moduli 1, 2, 3, 1, 2, 3, 1, 2, 3. That if you consider trying to take the means of those, besides whether or not they cross the modules and whatnot, their averages are in the middle, and the either terms that multiply together they're not in different widths in the pyramid. They're just like these pillars and rows. So besides when we're talking about all the numbers are large, sometimes we're dealing with models and numbers that are just some few in a row, and they're finite, and they just reflect a rotation and stages of the or stations, and are modular like a clock and rotate around. These are the kinds of things that make for these otherwise same kind of laws, and these inequalities about what they would make so. And as an example, besides the infinite case, in various spatial concerns, we can talk about the semi-infinite and doubly infinite and having spaces and doubling spaces. This is a kind of a thing. Then about the factorial, it's also reflects that is the very simplest expression in a production that has as an expression in the production, an element that's the index of the production. Similarly, that the sum of the first n numbers is n plus 1 over 2. Here it's described that the product is less than this quantity to the nth, is helping establish that these are pretty regular relations that would become very facile just in terms of looking at things defined in terms of these operations together and whether squares and stuff exist, that over time such a methodology can be put into place. I study mathematics a lot or all the time, but I'm just reading this book in this talk, so I can't really get into quite yet all that would entail. But in this second course of descriptive differential dynamics, its salience is fungible. Problem 7, use the inequality of previous section to show that if the a sub i's are greater than 0, then the sum of the a sub i's times the sub of the one of the a sub i's, with a to the negative i's, is greater than or equal to n squared. So again, this is the kind of back to the first case, the 1 plus 1 over x, and then the idea of about when they're equal, and then the idea about the operators and the sums, and then those relating to the property of the other operators in a field like algebra, or otherwise when they're defined in terms of each other, and otherwise when they're not, and otherwise when in the deconstructive accounts they come together and meet in the middle, or whether in the deconstructive account they start in the middle and come down and out like the standard is, and how our numbers start and come from and go. That just reflects that besides the fact that you might as well just start with the integers and then make the rest of the numbers make integers. So he defines the absolute number. So it's basically for a number represented in sign magnitude, it's the magnitude. The absolute value of x equals root x squared. And then he talks about x minus y and the absolute value of x minus y and the signed and unsigned. Whether or not in the real universe, in the continuous long lines, hologrammatic linear continuum, that is the numerical resource of a continuous domain that reflects the entire space-time, for example, and whether it's unsigned or signed quantities, it usually is reflected that it's unsigned. There's signless magnitudes first, and then on those live signed quantities. Usually on our real number line, we have it, there's unsigned quantities, and we just restrict that. We have an embedding of this unsigned quantities in those. It comes around and goes around. Hey, well, have a great day. We've about made it to the end of this chapter. It says that it is important to note that a single inequality, such as absolute value of x is less than the absolute value of y, is equivalent to two simultaneous inequalities. And so that gets into a lot of different notions about negations and the composition of yes, no, maybes, or sure, no, yeses, and these kinds of things in terms of then what makes for expressions that can then be combined and that can be evaluated in parallel, which make for how these things can, besides being derivable and provable and fungible, then become tractable and efficient and worthwhile to have a description of how to do them to save time. Well, anyways, hey, have a great day, and and I hope you have a wonderful day. Thank you.